Hi, hello, and welcome. I'm Greg Jacobs. I teach at Woodbury Forest School, a boarding school for boys in Central Virginia. If you have a younger brother who loves science, tell him to take a look at us. I would love to see him living in our dorms, performing on our athletic fields or on our stage, sitting in the desks behind this camera. But alas, all of those places are very empty right now. I'm so glad to have so many folks figuratively behind my camera. The AP exam is now less than a month away. I've been asked by a number of students lately, how many practice tests should we do? 10, 15? Where do I get more problems? More. I appreciate the enthusiasm and dedication. Really, I do. I love physics too. But that's not how to study for a cumulative exam. See, folks, I'm an old marching band guy. Kentucky State Champions, 1990. Look it up. Our director would tell us before every practice run through, practice doesn't make perfect. Perfect practice makes perfect. It didn't matter how many times we ran through our show if we didn't put our whole hearts and souls into each run through, if we didn't carefully identify mistakes to improve upon, or if we just went through the motions because Bosco Brown demanded that we do so. Yes, that was the name of one of the directors, a more American name I have never known. If you're watching this, you're likely taking several AP exams next month. Are you really going to do 10 practice exams for each of them? And if so, when are you going to sleep? When is your mind going to take a rest? Folks, don't make promises to yourself that you can't keep and that are detrimental to your progress anyway. Do a few practice problems, like one free response or a few multiple choice every day at most. But then look carefully at the solution. Whatever you got wrong, ask questions of friends and teachers until you understand. Write out a better response again. Engage with the problem until you can explain it thoroughly to another student, and then do so. That's what perfect practice looks like. Do that a bit every day, spending less and less daily time as the exam approaches, and you'll be very confident going into May 14th. Today, folks, we are going to talk specifically about energy bar charts. Here we go. This is our outline for today. I'm going to start by showing you some facts. This is the fact sheet that I show my students about energy. You can get a copy of my fact sheet via a link that I sent out on Twitter and through my blog. You can take a screenshot of this for use later in the lesson, but understand that we need to know the definitions that are on your screen right now. One of the things that I like to do with my class, especially when we're doing in-person review, is to give a little quiz about these facts. Not to see, not to shame anybody, you don't remember this, but to say, okay, let's know what we know and what we don't know. In fact, I gave a little quiz to my classes the other day. Normally, whoever gets the highest score gets to pick the music for our 90-minute classes. Well, I don't have 90-minute classes and we don't have any music for those classes. So instead, I offered to read names on today's show of the people who got perfect scores on the quizzes. And that was Jack Parrish, JJ Rivera, Logan McNabb, and Connor Liu. Nice work. Use this, but this isn't what we're talking about today. We're talking about energy bar charts. I'm going to be doing a lot of writing for you today. So I'm going to be using the document camera, and I'm going to be demonstrating something here, and then I'm going to be drawing an energy bar chart for you. Energy bar charts are the way to understand energy graphically. Tomorrow, we're going to have the second half of our energy show. Tomorrow, I'm going to show you how to use energy bar charts to do specific problem solving. But today, I just want to go through a bunch of situations and talk about how to create the energy bar chart. Now, many of you may never have heard of an energy bar chart. That's common language throughout the physics world, but you might have heard of an LOL diagram or an energy pie chart, or even just a statement of conservation of energy in words. Those are all fine. You don't have to use the techniques I'm showing you, but I'm showing you how they work because too many people dive into equations and problem solving before they've taken stock of what energy forms are in a particular problem. So let's do a couple energy problems to start with. I have here a cart attached to a fan, and I'm going to snap my fingers twice, and I want to keep track of the forms of energy between the two snaps. Ready? Right now and now. When I make an energy bar chart, first thing I need to do is define the system or object that I am considering. Sometimes the problem will tell you which system or object you must consider. Sometimes you have to choose. Today, right now, I'm telling you, we are considering the cart only. That is our object or system. Now, I need to consider what two positions am I drawing my energy bar chart for? Position 1 and position 2. That was the first snap and the second snap. Then I make a column for the work done by external forces, and I label the forms of energy that the cart could have at positions 1 and 2. But because this is a cart by itself, the only form of energy that it could possibly have is kinetic energy. Wait, you say, what about gravitational potential energy? Can't have it because it's a cart only. Potential energy requires an interaction between two objects in a system. Don't worry about that if you don't understand it yet. I'll get to potential energy in a few minutes. Right now, we're drawing an energy bar chart for the cart by itself. The cart can only have kinetic energy. Let's draw a bar chart. Did the cart have kinetic energy the first time I snapped my fingers? Yes, it did, because it was moving. So I'll annotate my bar chart, and I'll put, I don't know, 1 bar there. Doesn't matter how many bars I put there for now. There's just 1 bar there. Okay, at the second snap, I know the cart was moving faster. So that means I have to have more bars of kinetic energy. When I first draw a bar chart, don't worry about precisely how many bars should I draw. That's the horse caught between 2 barrels of water and doesn't know which way to drink. You'll freeze yourself. You won't know how to draw a bar chart at all, so you'll give up. Just draw something. Well, it's moving faster, so it has to have more bars of energy. Let's call it 3 bars, just for the heck of it. Okay, what about this work done by external forces term? Well, I don't know anything about that yet, but I can figure it out by writing a conservation of energy statement, which I write as bars plus bars equal bars. What does that mean? Well, how many bars were here? 1. I don't know how many bars there were in the work done by external forces column, but I do know that I put 3 bars there. So that means there must be 2 bars of work done by external forces. Is this energy bar chart to scale? Probably not. But does this give us an idea that the cart gained kinetic energy from positions 1 to 2, and the way the cart gained kinetic energy was because work was done by an external force? Now we can start talk about what does that mean, work done by an external force? If I do a Freebody diagram of the cart down here, I will see that there is the normal force, the force of the track on the cart. The cart was moving to the right, so the fan was pushing to the right because the cart was speeding up. And of course, there's the weight, the force of the earth on the cart. Work is done by a force when that force is acting in the direction of motion. So the motion was to the right. Therefore, the normal force did no work. The normal force was perpendicular to the motion. The weight, the force of the earth, did no work because the force of the earth was perpendicular to motion. The fan, though, did do work because the force of the fan was parallel to the motion. So this work done by external forces was a result of the work done by the fan on the cart. Wonderful. Let's do another one. This time, the cart's going to be moving that way. There's my 2 snaps. One more time, I'll do it again. The fan's pushing that way now. The first snap, the cart was moving that way. The second snap, the cart was still moving that way, but slower. Let's draw an energy bar chart for the cart only. Okay, what forms of energy do we have? It's a cart only, so I can only have kinetic energy. At position 1, the cart had some kinetic energy. I don't know how many bars. Let's call it 4 bars of kinetic energy. I'm just making that up. How do I know there was kinetic energy, though? The cart was moving. Kinetic energy is 1/2 mv squared. So if the cart has speed, the cart has kinetic energy. At position 2, the cart was moving slower. So let's put it, I don't know, 1 bar of kinetic energy. How much work was then done by external forces? Bars plus bars equal bars. That is a statement of conservation of energy in a weird way. 4 bars plus how many bars equal 1 bar? Well, mathematically, 4 plus -3 equals 1. What does that mean? Well, graphically, it means I need 3 bars below 0 of work done by an external force. Well, once again, let's look at the situation. The fan was pushing one way, but the motion was the other way. Fan was pushing one way, the motion was the other way. Therefore, the fan was pushing in the opposite direction of motion. When a force is acting opposite to the direction of motion, that force does negative work, and that's represented here. Careful, the negative sign on work does not mean work done in a different direction. Work and energy are scalars. They have no direction. So when I say negative work, that simply means the force is opposite the direction of motion. All right, let's do something not more interesting, but something a little more dramatic. I tell you, at the end of the show today, the last couple experiments I'm going to do, so you know, I'm going to be finding the spring constant of this spring. While I'm doing this, just a little tease, consider how you might find the spring constant of this spring experimentally, and consider how long it might take you to do so. Just think about it, because I guarantee you I can find the spring constant faster than you can. Think about it. Okay, here's our new problem. I'm going to let this go from rest. The fan is off. The fan is off. And I'm going to let it go from rest. There's position 1 at rest, and position 2 is right before the cart hits the bottom. I want an energy bar chart for the cart by itself. Why do I keep doing the cart by itself? You're going to find that I want to do the cart Earth system most of the time. This is the last cart by itself that I'm going to do. Position 1 is the top. Position 2 is the bottom, right before the cart hits that thing at the bottom there. Cart only can have kinetic energy. The cart was not moving at the top, so has no kinetic energy. The cart was moving at the bottom, so I don't know, call it 2 bars of kinetic energy. So how much work was done by external forces? Bars plus bars equal bars is a statement of conservation of energy. I have 0 bars plus question mark equals 2 bars. So there must have been 2 bars of work done by external forces. What force is applying the force that does work? All right, well, let's see. Here is a free body diagram of the cart. We have the normal force, and we have the weight, which I'm going to break into components. Sign slides. These are all the forces acting on the cart. The motion was this way. So the normal force does no work because the normal force is perpendicular to the motion. This component of the weight does no work because this component is perpendicular to motion. But this component does positive work because this component of the weight is in the same direction as the motion, hence positive 2 bars of work. All right, let's do something a little more difficult. Same situation. Cart released from rest here and ends up down here. I want to draw an energy bar chart for that same situation, except this time I'm going to draw an energy bar chart for the cart Earth system. I'll bet the Twitter feed is full of people asking, why don't I have potential energy in there? If you want to get on my Twitter feed, it's at Jacobs Physics. Feel free to ask questions. The last thing I'm going to do is take some questions from the crowd. But here's the answer. The CART-Earth system allows me to include gravitational potential energy. Position 1 to position 2, a CART-Earth system can have both kinetic energy and gravitational potential energy. Gravitational potential energy has the formula mgh, but all that means is that an object has gravitational potential energy if it has an h, a height above the lowest point. That h is measured vertically above the lowest position that you consider. So at the top, this had no kinetic energy because it stopped. Had some gravitational potential energy. How do I know? I'm just going to make it 3 bars randomly because the height was above the lowest point. Okay, was there work done by external forces? I'll hold on that. Was there kinetic energy at the bottom? Yes, because the cart was moving. Was there gravitational potential energy? No, because the height was at its lowest point. So how many bars of kinetic energy do I have? I don't know whether there's more than 3, less than 3, or equal to 3 until I consider the work done by external forces. Let's go down here and draw a free body diagram again. Wait a second, mg is the force of the Earth on the cart. The Earth is part of our system. The Earth is part of our system. When I say cart-Earth system, that means I can only consider work done by other forces than the other objects than the Earth in my column for work done by external forces. So it's not that the weight doesn't do any work, it's that that work is done internal to the system. So the normal force is the only force that matters here. Since the displacement, the motion was this way, the normal force is perpendicular to motion, and so the normal force does no work. Neither of these forces does work by an external force. So 0. That means I know I need bars plus bars equal bars. 3 bars here plus 0 bars here equals 3 bars here. That means 1, 2, 3. All right, why am I doing all this? Why? Who cares? Well, partially because tomorrow we can talk about using these energy bar charts to do problems, to make actual problem solving methods here. But I want to show you that we can solve some simple AP problems with just a bar chart, with no equations, no nothing. Just a bar chart. Let's take a look here. This is a problem from the Release 2014 exam. I graded not this problem, but a different problem, but I heard rumors that I'm sure are not true, that students like to draw animals on this particular problem, and especially sharks, where it says water surface. So they put a little shark here, and oftentimes that shark would be labeled like Mr. Johnson or something like that. I can't imagine that anybody would do that, but I heard things. Anyway, we're trying to draw an energy bar chart for the person from position A to position B. Now, this is important because this kind of problem is important. The question is, why would I use an energy bar chart instead of kinematics, instead of momentum? Well, momentum is used when something collides. Kinematics can be used anytime the free body diagram doesn't change. And in fact, in the first 2 problems that I gave you, the free body diagram doesn't change. The acceleration is constant. So whatever I was asked for, I could have used kinematics unless I was explicitly asked to use energy. But for this guy, kind of like this string here, anytime you have an object on a string that's moving not in a straight line and has a different free body diagram, whether you're talking about point A or point B, well, then energy is a good way to go. The canonical situations in which you must use energy and that kinematics and forces are not the correct way to approach it is object on a string, object on a spring, and an object on a curved track like a roller coaster. So here, this Tarzan problem, I really should be dealing with energy. So let's make an energy bar chart for this person from position A to position B. I'm going to have to go to my document camera here. Notice that position A and position B are both above the water's surface. So let's use the person Earth system. Why? Well, the problem asked us to, but even if the problem didn't ask us to, if you have a choice, try to use an object Earth system. This is point A and this is point B at the bottom and at the top. So that's A and this is B. Okay, person Earth system could have gravitational potential energy and kinetic energy. We know that at position A, the person was released from rest. At position B, or at position A, we know that there was some gravitational potential energy. Let's call it 5 bars. Why not? Because it's at a height above its lowest point. Where is that lowest point? I wish I could poll the audience right now, because in my class, I say, where do you want the lowest point to be? 1 through 5, the lowest point is point B. 6 through 10, the lowest point is at the surface of the water. It is 8. So the lowest point is at the surface of the water. It doesn't matter, is my point. The lowest point is at the position of the surface of the water. So that means at position B, the cart has, or the person has some gravitational potential energy. I'll call it, I don't know, 2 bars, still above surface. The cart is moving, so it has some kinetic energy. I don't know how much, but I can talk about the work done by external forces. Once again, I draw a Freebody diagram. I know that at point A, the tension in the rope is like that, and at point A, the weight, the force of the Earth on the person is like that. The Earth is part of the system. So mg cannot contribute to the work done by external forces. The tension is not part of the system, so the tension could do work. But since the motion at position A is that way, the tension is perpendicular to the motion. And that's true anywhere. Wherever you consider from A to B, the tension is always perpendicular to the direction of motion at that instant, because the radius of a circle is always perpendicular to a tangent to the circle, if you want to think of it that way. Point is, the tension can do no work here, and therefore, no work is done by external forces. Conservation of energy statement. I've got 5 bars here plus 0 equals 5 bars. So I've got 2 bars here. I must have 3 bars of kinetic energy. Let's talk about what actually happened here. These bars must have the same numbers on both sides, so any loss of bars here with no work done by external forces must result in a gain of bars here. We lost 3 bars of gravitational energy. Those went into 3 bars of kinetic energy. Gravitational potential energy was converted to kinetic energy. Could I have done the same problem with the lowest point being point B? Absolutely. Forget about the water. This object only goes from A to B. It never gets lower than point B. So let's make this the lowest point, point B. Still no work done by external forces for the same reason as before. But this time, there's still no kinetic energy at A. But this time, the gravitational potential energy at B is 0. And we know that there is kinetic energy at the bottom. Since before, in the previous chart, I had 5 bars of gravitational energy dropped to 2 bars of kinetic energy. That is, we lost 3 bars of potential energy from here to here. Well, we still need to lose the same 3 bars of potential energy from here to here because we're losing the same amount of height. mgh is the formula for potential energy gravitationally. So I must have the same change in gravitational potential energy. So I'm going to put 3 bars to keep this to the same scale. And it's moving how much kinetic energy? 3 bars. How do I know that? Because bars plus bars equal bars. 3 plus 0 equals 3. All right, wonderful. Time to do a couple questions that you can do without any calculations with an energy bar chart. Let's look. Yeah, we'll do this one and then that one. A rocket is firing its engines as it speeds up away from Earth, and that's all we need to know. The question is, what happens to the mechanical energy of the Earth rocket system? Does the kinetic energy increase or decrease? Potential energy increase or decrease? Mechanical energy increase or decrease? This is an authentic AP exam question. We can answer it with just an energy bar chart. As I told you, always want to use the Earth rocket system if we can. So this is at the at launch, and this is 1 kilometer high. We can have kinetic and gravitational potential energy. At launch, there was no kinetic energy because it started from rest. We can call this the lowest position when we launched the rocket. 1 kilometer high, it is above its lowest point. 1 kilometer high, it said that, so there must be a height and therefore a gravitational energy. Kinetic energy, there must be some because it's moving faster. It said the rocket sped up as it moved away from Earth. I don't know, I'll call that 3 bars. How much work is done by external forces? Well, bars plus bars equal bars. Must be 5 bars of work done by external force. What is the external force that does the work? We draw a Freebody diagram. We've got the force of the engine on the rocket and the force of the Earth. This is part of our system, so does no work. The force of the engine is in the direction of motion, so can do positive work, and that is the work done by the engine. Okay, that doesn't answer the question yet. The question, if you recall, said, what happens to the kinetic energy of the rocket? Increases. Potential energy of the rocket increases. Mechanical energy of the rocket. Mechanical energy is defined as kinetic plus potential energy. That's the definition of mechanical energy. Initially, we had no mechanical energy. At the end, we had 5 bars of mechanical energy. Therefore, the mechanical energy increased. One more problem before I move into springs. You figure out how you're going to measure the spring constant of that spring. I'm going to do it in like 10 seconds, by the way. It's going to take me 10 seconds to find the spring constant of that spring from once I start collecting data. I don't think you all believe me, so I'll just have to show you later. One more problem. Here it is. This is the one that Josh showed you at the end of his class yesterday. A student is moving the box from ground level to the top of that platform, and the student is pushing up an incline in figure 1 and going straight up in figure 2. And the question is, in which case does the student do more work on the box? Justify your answer. All right. Let me do it on one more bar chart here. Again, student Earth system. And we'll go from the floor to the ramp. And this will be when he goes straight up. And this will be when they go at an incline. I'll do two separate energy bar charts. Since we're a student Earth system, we can have both kinetic and gravitational potential energy. And we've got to make some assumptions. I'm going to make the assumption that the student starts the box from rest and ends the box at rest. If you want to make the assumption that the box is moving at constant speed the whole time, you get the same result. But I'm going to assume no motion at the beginning and no motion at the top. And that's true whether we go up an incline or whether we go straight up. We had to start the box from rest and end the box at rest at the top. So for the same reasons, I've got no motion, no kinetic energy. From the floor, let's call the bottom of the floor, let's call the floor height equals 0. Well, that's the same no matter whether there's a ramp there or not. Okay, gravitational potential energy, the formula for gravitational potential energy is mgh, where h indicates the vertical height above the lowest position. Well, they told you we were going to the same loading dock either way. So the height above the floor is the same either way. So that means the same gravitational potential energy either way. That means when I do bars plus bars equal bars, 0 plus equals 2. So that must be 2 bars. And the same thing here, 2 bars. Either way, the student has to do the same amount of work to get this object from the floor to 2 bars of gravitational potential energy. I don't have to do any math. All I have to do is know the definition of the H term in gravitational potential energy. I have the same amount of work done either way. Isn't that amazing? All right, enough with the energy bar charts for a moment. It is time to figure out the spring constant of this spring. Springs are important because I'm going to bring up the potential energy due to a spring in a few moments. But right now, I just want to know, how would you determine the spring constant of a spring? Well, the formula for the force of a spring is F equals Kx. So if I plot a graph of the force applied by a spring as a function of the distance the spring is stretched, then it will be a straight line with slope K, because I could circle y equals mx plus b. This is the y-axis. This is the x-axis. So what's left is the slope. So I'm going to do that. I'm going to make a graph of force versus distance, and I'm going to take the slope of that graph to represent the spring constant. Except I'm going to do that very quickly. Here is a force probe. Here is a spring. I'm attaching the spring here. And then I'm going to attach the spring to the cart, and I'm going to tell my thing to collect. And this thing, this cart can say not just what the force is, 20 times per second, but also how far the cart has moved from its original position. So watch this. I'm going to have to put you on the camera again. You notice that I have force on the vertical axis, position on the horizontal axis. I'm going to make sure my force probe is zeroed to start. And I'm going to zero my position sensor right about here. And let's go. Oh, look at that. Take the slope, I get 12 newtons, 12 newtons per meter. That's the standard units of a spring constant, 12 newtons per meter. I did that in just a couple seconds. I said 10 seconds. I probably did it in 5 seconds. That's just an elegant way of finding the spring constant. So why did I do that? I thought this class was about energy. Well, 2 things. Let's talk about an energy bar chart for that cart when I moved it from its original position here to its final position there. Let's do an energy bar chart for the cart only. And I'll tell you why in a moment. It's from position 1 to position 2. Card only can only have kinetic energy, had no kinetic energy at either position. But that's weird. Oh, because I was touching it. That's going to be too confusing. Sorry. I meant to do the cart only system. I want to do the cart spring system, and here's why. We had to include the work done by me, and I don't want to mess with that. The cart spring system. Let's do it this way. The cart spring system, since this is a system consisting of more than just the cart, I can have a potential energy. But that's not gravitational potential energy. We're on a level surface. There is no change in gravitational potential energy. That's spring potential energy. We had no kinetic energy at either position because it was not moving. The spring potential energy has a formula. 1/2 kx squared, where k is the spring constant of the spring and x is the distance the spring is stretched from its equilibrium position. In the first case, the spring was at its equilibrium position, so had no spring potential energy. But in the second case, the spring was stretched. So let's just give it 4 bars of spring potential energy because x was not equal to 0. So there must have been work done by an external force. What is that external force? Well, that is me pushing. I was pushing in the same direction that the cart was moving. Therefore, how much work did I do? 4 bars. The work that I did went into creating spring potential energy because the spring was compressed. Now we have one more fact on that equation sheet. You might have learned that work equals force times distance. That's correct in the case of a constant force. Notice that I've made no reference to that all day. In the case of a constant force, work is force times distance. In the case of a not constant force, you have to take the area under a force versus distance graph. So the work done would be the area under that graph, which happens to be equal to the spring potential energy in this case. So my question is, if I use a stiffer spring, and I'll leave this right there. Here is a stiffer spring. I know it's one that it's harder to pull, takes more force to pull the same distance. What should that graph look like? Well, I should have to do more work because there's going to be more spring potential energy when I stretch this the same distance. Or you can think of it, so there's needs to be more area under the graph. Or you could say the slope is the spring constant. A stiffer spring has a bigger spring constant, so I should have a steeper slope. In either way, whether we reason from force or from energy, we should find a steeper graph here. And let's try that. Trying to hook this on. There we go. And let's zero this guy here and go. Oh, and I let it go. So that was when I let it go at the end and had some force on there. But there, 34 newtons per meter. Clearly a stiffer spring, a steeper graph than the first one. Physics works, and I love it. So let's take some questions. If you would like to ask a question, go to Jacob's Physics and switch camera. There we go. If you'd like to go to Jacob's Physics at Twitter, then I'll take a few of your questions. I got about 5 minutes. Let's go. For the review problem yesterday, should it be the box Earth system? You can use any system you want. I prefer to use the box Earth system. You could have used the box by itself, but then you would have had work done by the person that is external to the object, and you would have had work done by the Earth. The Earth was pulling down, the object was moving up, the motion was up, the Earth was pulling down. A force opposite the direction of motion does negative work, and you would have had to include that. That's complicated. That's why I say use the box Earth system, and then the work done by the student just pops out as the only work done by external forces. Thank you. That was Mike who asked that question. Let's see. It was the, I hope I didn't say student Earth system. It was the box Earth system, but whatever I said, I hope I said it right. Would we construct, this is Tarun who's asking, would we construct an energy bar chart in the experimental design portion of a free response, or would it be in place of a graphing component in an energy free response? And remember, we don't have an experimental design, but the question could still be asked about a qualitative quantitative translation. Should we construct an energy bar chart, or should we do something else? A lot of times a problem will ask you to derive an expression. Derive an expression for the speed of this cart if I pull it back a certain distance and let it go. We're going to do that problem tomorrow. When you're doing that, the first step is an energy bar chart. Once you write an energy bar chart, you're going to find that any other question that can be asked is trivially easy, because you're going to use the energy bar chart to write an equation and then to solve that equation for whatever you want. So the answer is yes, start with the energy bar chart. Energy bar charts are like Freebody diagrams. If you know it's a force problem, you draw a Freebody diagram before you do anything else. If you know it's an energy problem, draw an energy bar chart before you do anything else. If you draw LOL charts or if you draw pie charts, that's fine too. If you just write out in words what the energy conversion is, that's fine too. I like the energy bar chart because it provides a structure that is very similar across any kind of problem that you could use. Prabhev says to find the spring constant, he would use the energy conservation of the spring, like I was just discussing, measure the velocity using the motion sensor. Yeah, I can do that. I'm going to go the other way tomorrow, knowing the spring constant, predict the speed. But you could have done that, absolutely. There's nothing wrong with that. The AP exam will not ask you, hey, we're going to give an extra point to the person who can do this in 5 seconds. I was just doing that because it's fun. There are a million ways to discover spring constants. Prabhav used energy. You can use just F equals Kx by hanging weights from the spring. You could use a spring scale to measure the force and plot that versus displacement. There's a million ways to do it. I just chose this one because it was fast, easy, and you could see it on my iPad. And let's see here. Hannah says, does negligible friction mean there is no friction or there is friction but you can ignore it? Either of those answers is equivalent. Doesn't matter. There is friction, but you could ignore it. This track is pretty darn low friction, and anything I do with this track and these kinds of carts, friction is negligible. Does that mean that if I got extra sensitive things that I couldn't measure a friction force? Well, I don't know. Depends on how sensitive your probes are. But for all intents and purposes, we can neglect friction the same way we can neglect the force of Jupiter on the cart. Oh, it's there. The force of Jupiter on that cart is there, as Josh told you on Monday and Tuesday, GMM over D squared. But we don't care because that force is so small compared to the other forces acting that the force of Jupiter is negligible. All right, one more here. I missed it. Let's go here. Okay, shouldn't the work on the ramp be more than the work going straight up because the ramp is a farther distance? Remember, when we use the formula work equals force times distance, A, we need a constant force, which we have here, and B, you have to consider the force that is acting parallel to the direction of motion. If we're going straight up, then in equilibrium, I have to apply an upward force equal to the weight of the cart over the vertical distance. If I push along the ramp, then to keep equilibrium, I only have to push with a force that is equal to the component of mg along the incline, mg sine theta. So I have to apply a smaller force. I am going a bigger distance that's parallel to that force. And it's hard to figure out whether those two effects cancel out. Smaller force, bigger distance, bigger force, smaller distance. It's hard to figure out whether those cancel out unless you use the energy bar chart for the object Earth system. All right, then. I'm going to show you. Stop this share and go to another share. Here is problem for tomorrow. Tomorrow, I will be with you again. Josh is back on Friday, and I will be doing some more energy bar charts, except this time we're not going to stop at the energy bar chart. We are going to continue and make some calculations, make some explicit experimental predictions that we can measure in the laboratory. And tomorrow, Edna's going to get to ride. All right. I will see you tomorrow. Thanks for everybody for watching. So long, everybody. Good night, Edna.